بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is section 2.4, special functions and their graphs. Uh, starts by application preview. It is important here to pay attention to the definition of the average cost function. So we know the cost function. We studied the cost function. So for example, this is a cost function of degree 2. The average cost will be denoted by C bar of x, and the definition is it is the total cost over x. So you just divide the total cost by x to get the average cost function. Now, if you divide the cost function by x, you can here distribute the numerator over the denominator. So you can write it 900 over x plus 3x over x plus x squared over x. And then it is 900 over x, or if you want to write it 900 times x to the power -1, and x cancels with x, and x squared over x is x if you subtract the power. So this function here is not a polynomial function. The cost function is a polynomial function, while this function is not a polynomial because x has power 1, in power -1. In polynomials, the powers should be 1, 2, 3, 4. It cannot be -1. So this is one of the functions we are going to study in this section, and special functions, which is the rational function. Let us start by very basic functions. This function f of x equals x is called the identity function because it sends each number to itself. So f of 1 is 1, f of 2 is 2, f of -1 is -1. So the graph of this function is this line. It's a straight line, y equals x. It passes by the point 0, 0, 1, 1, 2, 2, -1, -1, and so on. The second function is the constant function f of x equals c or y equals c, where c is just a real number, 1, 2, 3, 4, -1.5, whatever. So this is called the constant function. Why we call it constant? Because, for example, for this function f of x equals to 2, if I ask you what is f of 1, your answer should be 2. What is f of a? Your answer should be 2. What is f of x plus h? Your answer should be 2. So the answer is always 2 because it's constant. The output only consists of 2. So if you have an input-output machine, the output is always 2. The input could be any real number, but the output is always 2, one output only. That's why they call it constant function. The graph of a constant function is a horizontal line. So y equals to 2, the graph is this horizontal line. So any constant function, the graph is a horizontal line. If I ask you to find f of 0, this is 0, you go up, f of 0 is 2, f of 1 is 2, f of 1.1 is 2, f of 2.5 is 2, f of any number is 2, that's the constant function. The slope of the line y equals to x is 1. The slope of the horizontal line is 0. The slope of the horizontal line is always 0. The third type, the power functions. The power functions are functions of this form, a times x to the power b, where b is positive. We don't need b to be negative here because if b is negative, you know the definition of x to the power -n, it's 1 over x to the power n. So x to the power -1 would be 1 over x. X to the power -2 would be 1 over x squared. So if you have a negative power, then you don't have x to the power b in the numerator. You have it in the denominator. And if you have it in the denominator, it would be a rational function, not a power function. So to keep it power function, B, the power of x has to be always greater than 0. Examples, you have x squared, a is 1 here, and b is 2. Y equals x cubed, b is 3, and a is 1. So we have functions like this, x squared, x cubed, x4, x5, and also we have roots, y equals x to the power half or square root of x. Remember, when you have the nth root of x, this can be written as x to the power 1 over n, 1 over n. And the nth root of x to the power m can be written as x to the power m over n. So when I say to you 1 over 2, x to the power half, this is the square root of x. Third root of x would be x to the power 1 over 3. So notice here that the powers are greater than 0, but less than 1. Less than 1 half, 1 over 3, 1 over 4, 1 over 5. So these functions, square root, cube root, are also called root functions. So they are power functions and root functions, while x squared, x cubed, x to the power 4 are also called polynomial functions. Some type of the polynomial. The polynomial functions are more general than this, but they are polynomial functions, and at the same time, they are power functions. There is a difference in the graph of this of the root function and the polynomial function. For x squared, this is the graph of y equals x squared. It's a parabola. We studied parabolas. The vertex is 0, 0. Y equals to x cubed has this graph, okay, always increasing. The domain or real numbers, the range or real numbers. While here, x squared, the domain or real numbers, but the range is from 0 to infinity. So this is x squared, x cubed. X to the power 4 would be similar to x squared. Okay, x to the power 4 will go just like this, more flatter, more flatter than x squared. X to the power 6, x to the power 8 are all also similar to x squared, just more flatter. And they come closer also to the y-axis. So x to the power 4 would be something like this. It starts from here. Yeah, it's closer to the y-axis than x squared. So this would be x to the power 4. And x to the power 6 would be more closer and so on. But they have uh, the same, almost the same shape as x squared. X cube is like this. X to the power 5 would come from here and it will go flatter, flatter, and go like this. So this is x to the power 5, for example. 7 the same, 9 the same, but also flatter and become closer to the y axis. So the main two, x squared and x cube. Square root of x, now the root function, this is the graph of square root of x, the domain from 0 to infinity, and the range is also from 0 to infinity. While cube root of x has this graph and the domain or real numbers, the range or real numbers, where there is no problem that x is negative here because cube root of -1 is -1, cube root of -8 is -2, and so on. So there is a difference between square root and cube root. You notice that uh, the bending, the shape, okay, look to the shape, uh, the difference between x to the power b when b is greater than 1. So x squared like this, x cubed like this, x to the power 4, they bend upward, okay, upward. So always concave up. The graph is like this, concave up. Y equals to x is just a straight line if power 1. If b is less than 1, 0, so they concave down like this. So they bend down, bend downwards. This upwards, concave up, this is concave down. This is also a difference between the graph of the root functions and the polynomials. See here, concave down. Here, concave up. Okay, so put in your mind this difference between the root functions and the polynomial functions. Now for shifting, we studied the parabolas in 2.2, and we said that this parabola, for example, we can sketch the graph of this parabola by shifting the graph of the original parabola, which is y equals x squared, each unit to the right, each units in the x direction. If h is positive, then negative. If h is positive, then we have -1, -2, for example. We will go to the right. And if h is uh, positive also, and this is a plus h, we will go to the left. Plus k here, up if k is positive, down, okay, if it is minus k and k is positive. So let me give you some examples. For example, y equals x minus 1 square plus 3. Here we will go 1 unit to the right, 3 units up. So we sketch the graph of x squared, same graph, but we move 1 unit to the right and 3 units up. So 1 unit to the right, 3 units up, and we sketch the graph of x squared. All right, this is the graph of x minus 1 squared plus 3. Y equals x plus 2 square minus 1. Here we'll go 2 units to the left and 1 unit down. So 2 units to the left, 1, 2, and 1 unit down, and then we sketch the graph of the parabola. So the shifting is easy like this. So if we have an original graph of y equals f of x, we can sketch the graph of f of x minus h plus k, where h units in the x direction, right, left, and k units in the y direction, up and down. So for example, we know the graph of x cubed. What would be the graph of x cubed minus 3? Well, x cubed minus 3, we will go 3 units down. So the graph of x cubed, and you go 1, 2, 3, 3 units down, and then you graph x cubed. So this is x cubed minus 3. While b, this 2 here, we go 2 units to the right. So we from here, from 0, we go 2 units to the right and sketch the graph of x to the power 3. So this is x minus 2 to the power 3. And finally, C, we have 2 units to the right and 3 units down. So we go 2 units to the right, 1, 2, and then 3 units down, and we sketch the graph of x cubed. Now, polynomial functions have this form where the powers n minus 1 are positive integers. So in 1, 2, 3, 4, and so on, positive integers. We don't have power of half, for example. N cannot be half, or negative. N cannot be -1 or 2 or 3, or -2 or -3. If n is negative or rational, then it is not a polynomial, okay? Then the equation is not an equation, or the function is not a polynomial function. While these numbers, an minus 1, these numbers are the coefficients, and they could be any real number. So for example, y equals square root of 2 x to the power 4 minus, let me go, okay, minus pi x to the power 3 plus square root of 5, okay? This is a polynomial. Why it's a polynomial? Because we have power 3 and power 4, so positive integers. But these coefficients, square root of 2, pi, square root of 5, it's no problem. They could be any real numbers. They could be fractions, they could be roots, pi, e, whatever. Now, the linear function is a polynomial of degree 1, okay? And the quadratic function, which we studied also, is a polynomial function of degree 2. If a is positive, degree 2, we know that the graph of degree 2 polynomial is a parabola. If a is positive, the parabola opens upwards, and if A is negative, the parabola opens downwards. The number of turning points is 1. This is here a turning point. A turning point is a point in which the graph changes from decreasing to increasing or from increasing to decreasing. So this is one turning point and this is one turning point. So always degree 2 has one turning point. The number of x-intercepts could be 0, 1, or 2. So for example, I could have a parabola like this. So this is with 0 x-intercepts. I could have a parabola like this with 1 x-intercept, and I could have a parabola like this with 2 x-intercepts. If we talk about degree 3 polynomials, then the number of turning points, the maximum number of turning points is always the degree minus 1. So 2 is the maximum number of turning points for degree 3. Here the maximum number is 1, okay? And then if you want another numbers, you subtract 2. So the maximum number of turning points of degree 3 is 2 minus 2. Also, it could have 0 turning points. So look here for this is x cubed. This graph is always increasing, so it has no turning points, 0 turning points. While this graph, and notice that if A is positive, A is the coefficient of x cubed. If it is positive, the graph of x cubed would be similar to this n, uh, letter N in English, okay? And we have 2 turning points. But if A is negative, the coefficient of x cube is negative, negative x cube, negative 2x cube, the graph would be like this, reverse it, n, okay? And x cube, negative x cube, this is the graph of negative x cube. It would be like this. And it has no turning points because it's always decreasing, while here we have 2 turning points. So degree 3 could have 0 or 2 turning points, while for x-intercepts, I could have 1 x-intercept. I could have 2 x-intercepts, and I could have 3 x-intercepts. So degree 3 could have 1, 2, or 3 x-intercepts. Degree 4, the maximum number of turning points is 4 minus 1, which is 3. Subtract 2, they could be also 1 turning point. So there is a graph, or there are graphs of degree 4 polynomials with 1 turning point like this. Like I told you, this is similar to x squared, but more flatter and comes closer to the y-axis. Here, if A is positive, all of these graphs, if the coefficient of x to the power 4 is positive, while all of these graphs, if the coefficient of a to the power 4 is negative, the number of turning points could be 0, 1, 2, 3, or 4. So this, for example, 0, okay, turning points could be 1 like this, okay, could be 1 here, could be 2 like this, okay, could be 3, for example, 1, 2, 3, okay, 1, 2, 3 turning points, could be 4 like this, 1, 2, 3, 4, okay. So it depends, any number of x-intercepts up to 4. The maximum number of x-intercepts would be always the degree of the polynomial, because x-intercepts are the zeros of the function. So if it's degree 2, the maximum number of zeros would be 2. It could have 1 0 or no 0 like this. Let us solve this checkpoint. All constant functions such as f of x equals 8 have graphs that are what? Horizontal lines. Horizontal lines. So y equals to 8, the graph is a horizontal line. Which of the following are polynomial functions? The power is 3, 1, so this is a polynomial function. Here, if you distribute, it's x over 4x plus 1 over 4x. So here we can cancel x with x, so we have 1 over 4. So this is no problem. But the problem is here in this term, because this x in the denominator cannot be, we cannot erase it. You can write it if you like 1 over 4 and you take it up if you want. So you see that we have power -1. So power -1, this is not a polynomial. Here we have x to the power half. This is not a polynomial. Here we have x to the power half, 1 over this. You cannot cancel this root. Of course, you cannot cancel the root with the root because we have plus everywhere, plus here, plus here. So this is not a polynomial, while this is a polynomial because x has power 1. So the answer is A and E. These are polynomials. A third degree polynomial can have at most how many turning points? The maximum number of turning points is the degree minus 1. So 2 turning points. These are the rational functions. The easiest rational function is the function 1 over x. And for rational functions, the domain is not all real numbers. The domain of all polynomials are real numbers. See here, the domain always for any polynomial is set of all real numbers. But for rational functions, we know that the denominator, we cannot allow the denominator to be 0 because it's a math error. So uh, here the domain of this function would be all real numbers except 0. And also the range, okay, this is the domain. The range, if you look to the range, the y values, this is the y-axis, look to the y values. There is a graph everywhere except at 0. So the range is also all real numbers except 0. And if you look this, if you bring the graph to the y-axis, there is always a graph the y-axis is always there except this point where uh, uh, y is 0, it's not there. So the range consists of all real numbers except 0. Also, you notice that there are what we call asymptotes. This line is a vertical asymptote for this function because it approaches, the function approaches this line from the right and approaches the line from the left, but it never touches the vertical asymptotes. Also, this line is a horizontal line and it's a horizontal asymptote because the curve approaches this line when x goes to infinity. The curve approaches the line, and when x goes to negative infinity, the curve approaches also the line. So the graph of 1 over x has a vertical asymptote with equation x equals to 0. This is the equation of the y-axis, and the horizontal asymptote with equation y equals to 0. This is the equation of the horizontal asymptote. It is also called the reciprocal function, okay, 1 over x, and it's also a special rational function. A rational function in general is a polynomial over polynomial. So f and g are polynomials. Any polynomial over polynomial, we'll call it a rational function. Of course, the polynomial in the denominator cannot be 0. The domain of any rational function would be all real numbers except the zeros of the denominator, the zeros of g. Now, a vertical asymptote, a rational function always have a vertical asymptote if the vertical asymptote will have this equation, x equals to c. So x equals to c is the vertical asymptote. For example, here x equals to 0. Why 0? Because 0 is a 0 of the denominator. So to find c, you search for the zeros of the denominator, but you make sure that they are not zeros of the numerator. So for example, if you have x over x plus times x plus 1, okay, then here uh, at x equals to 0, there is a hole, okay, there is a hole, not a vertical asymptote, because uh, 0 is a 0 of the numerator and the denominator. We have x up and x down, while x equals to -1 is a vertical asymptote. At -1, we have a vertical asymptote. So x equals -1 is a vertical asymptote like this. This line is a vertical asymptote for this function, but at 0, there is a hole, okay? You see where is y, and you graph a hole like this. So differentiate between holes and vertical asymptotes. To be a vertical asymptote, it has to be a 0 of the denominator, but not a 0 of the numerator. For horizontal asymptotes, we have polynomial over polynomial. So we have degree of the polynomial in the numerator and degree of the polynomial in the denominator. If n equals m, which means they have the same degree, then the equation of the horizontal asymptote is y equals an over bm, the coefficient of the highest power over the coefficient of the uh, uh, highest power also in the denominator, in the numerator and the denominator. So for example, if the function is x squared minus 4 over x minus 2x squared, then here the line, this is the function, let me write it. Okay, f of x, let me just write it. F of x, you can write it y, of course, no problem. So the horizontal asymptote of this function would be y equals to what? Okay, y equals to what? The highest power is x squared in the numerator, and the highest power in the denominator is also -2. So what is the coefficient of x squared in the numerator? 1. What is the coefficient of x squared in the denominator? It's -2. So the line y equals to -half is a horizontal asymptote of this function. Okay, so this if you have same degree, okay, in the numerator and the denominator. While if the denominator, if the degree in the numerator is less, so n is less than m, degree of the numerator is less than degree of the denominator, then the line y equals to 0 is the horizontal asymptote, which is the x-axis, like the function 1 over x. What is the degree of the numerator here? The polynomial in the numerator has degree 0. Any constant has degree 0 because it's 1 times x to the power 0, and x to the power 0 is 1. So 1 is a polynomial of degree 0, x is a polynomial of degree 1. So uh, degree of the numerator is less than degree of the denominator. So the line y equals to 0, as we have seen, is the horizontal asymptote of this function. Another example, if f of x, for example, equals x over 3 minus x squared, then the horizontal asymptote in this case is y equals to 0, because the degree of the numerator is x, the degree of the polynomial in the denominator is 2. So the line y equals to 0 will be the horizontal asymptote of this function. While if n is greater than m, if the degree of the numerator is greater than the degree of the denominator, then there will be no horizontal asymptote. For example, f of x equals x squared plus 1 over 1 minus x has no horizontal asymptotes because degree 2 and degree 1. So these are the three cases for the rational functions. Let us have one example. This is an example. So if I ask you to find the equation of the horizontal asymptotes of this rational function, what do? You look to the polynomial in the numerator. What is the degree? It's 1. Okay, the polynomial in the denominator, what is the degree? 1. They have the same degree, so the horizontal asymptote has the equation y equals 12, the coefficient of the highest degree in the numerator, over 3, which is the coefficient of the highest degree in the denominator. So y equals to 4 is the equation of the horizontal asymptote of this function. While the vertical asymptote, to find the equation of the vertical asymptote, remember, we need it to be a 0 of the denominator, but not a 0 of the numerator. So we take the denominator, put it equal to 0. So 3x would be 9. And when we divide by 3, x would be equal to 3. So 3 is the zero of the denominator. Is it a zero of the numerator? No, because 12 times 3 plus 8 is not 0. So the equation of the vertical asymptote is x equals to 3, and the equation of the horizontal asymptote is y equals to 4. Let us try to sketch the graph of this function. X equals to 3, 1, 2, 3. Let me take the x-axis down because we will need to go up. Okay, 1, 2, 3, 4. So y equals to 4 is the horizontal asymptote, and 1, 2, 3, x equals to 3 is the vertical asymptote. So these are the asymptotes of this function. Now, to sketch the graph of the function, if you have power 1 and power 1, always the graph is similar to the graph of 1 over x. I mean, look, here you go to the vertical asymptote to sketch. This is the easiest way to sketch the graph of this function. Now this is a 3, this is x equals to 3. You ask for 4, okay? You put 4 here. So 12 times 4 plus 8 over 3 times 4 minus 9. What is the answer? Is it positive or negative? It would be positive, and it would be greater than 4. Okay, if you check, so 4 times 12, let me calculate, let me use the calculator. 4 times 12, 48 plus 8, so it is 56 over 12 minus 9, which is 3. 12 minus 9 is 3. The answer is, in fact, 18 point something, okay? So if x is 4, it's very up, okay? 18 point something. So the average would be, the graph would be like this. It becomes closer to the vertical asymptote, and also it becomes closer to the to the horizontal asymptote, to the vertical and to the horizontal, approaches them from here and from here. While so in this square, you can say that the horizontal uh, asymptote and the vertical asymptote divide the region into 4 squares. This is one square, this is the second, this is the third, and this is the fourth. Okay, the graph would be in 2 of these four squares. So this is 1 here. And if you choose a number less than 3, for example 2, okay, if you put 2, let me choose 0, because if I choose 0, I will get the y-intercept. If you choose 0, you get 8 over negative 9, which is somehow less than negative 1. So this point. So the graph will go from here and approaches the x-axis, not the x-axis, the horizontal asymptote, and also approaches the vertical asymptote like this. So the graph always approaches the horizontal asymptote and the vertical asymptote. So this is the graph of this function. If you want, let me give you another example. For example, let us sketch the graph of y equals 1 minus x over x plus 1. All right. What is the equation of the vertical asymptote here? X equals to negative 1 because it makes the denominator 0, not the numerator. What is the equation of the horizontal asymptote? Y equals negative 1 because the degree is 1, the degree is 1, so we divide the coefficient of x over the coefficient of x. So for this function, x equals to negative 1 is a vertical asymptote, y equals to negative 1 is a horizontal asymptote. So we have 4 squares, 1, 2, 3, 4. Where is the graph? You come to negative 1, okay? The vertical asymptote. Choose 0, a number to the right, a number to the left of the vertical asymptote. So 0 and negative 2. I'll choose 0. If x is 0, okay, I have 1. So here. So this point, the graph passes by this point and it approaches the asymptotes. So the graph would be like this. It has to approach the asymptote and pass by this point. Okay. So this is the graph in this part. If x is 0, sorry, if x is 0, yeah, the graph is 1. Good. Now, if x is negative 2, then I'll have 1 minus minus 2 positive, and negative 2 plus 1 is negative. So the graph would be negative here. It would be 1 plus 2, 3. It would be negative 3. So it becomes closer to this and closer to the asymptote, and it passes by the point negative 3. So this would be the graph of this function. I hope you understood this point. It could also, it could be the graph in this square and in this square. It doesn't have to be always in these two. For example, if I sketch the graph of y equals negative 1 over x. Well, negative 1 over x, uh, what is the horizontal asymptote? Y equals to 0 because degree of the numerator is less. What is the vertical asymptote? X equals to 0 because it makes the denominator 0. If I choose 1, okay, choose 1, it would be negative 1, so the graph is here. So the graph becomes like this, closer to these two asymptotes. And if you replace x by negative 1, negative 1 over negative 1 is 1, and the graph would go like this. So this is the graph of negative 1 over x. Okay. Given this function, decide whether the following are true or false. Vertical asymptote x equals to 4. 4 is a 0 of the denominator. It's not a 0 of the numerator, so this is true. X has a horizontal asymptote x equals to 3. The degree is 1 in the numerator, the degree is 1 in the denominator. Coefficient of x is 3, coefficient of x is 1, 3 over 1 is 3. So this is also true. Finally, the piecewise functions. Absolute value of x is a piecewise function because it has two pieces. It's x if x is positive, it's if it is negative x if x is negative. So if x is positive, then this is the graph. It has part of this graph y equals x. So y equals x in this interval, and y equals negative x in this interval. And when we put them together in one curve, in one graph, this would be the graph of absolute value of x. Notice that negative x here is a positive number because x is negative. So if x is negative, then negative x would be positive, and we need the absolute value to be always positive. So for example, absolute value of negative 3, we cannot accept it's equal to negative 3 because it would be negative. So we have to multiply by negative. So x here is negative 3, and negative x, I mean negative x is negative 3, negative x would be positive. It would be equal to 3. For example, we have a piecewise function like this. How to find the values? F of negative 5, you have to see x is negative 5. Is negative 5 less than 0, between 0, 5, or greater than 5? It is less than 0, so f of negative 5 is just 5. F of 4, look to 4. Where is 4? It's not less than 0. It's between 0 and 5. So you use this definition. So f of 4 would be 2 times 4, which is 8. F of 20, 20 is greater than 5. So I use this definition. So 20 plus 6 is 26. If you want to sketch the graph of this function, this graph has three pieces. Less than 0, less than 0, the graph is 5, constant function, 3, 4, 5. So the graph like this, to the left of 0. And this point is with me, so I'll keep it closed because the equality is here. So f of 0 is 5, okay? While from 0 to 5, it has the line 2x. So at 0, it would be 0. but I'll put an open circle. And at 5, 2 times 5 is 10. So 1, 2, 3, 4, 5, it's 10 somewhere here, okay, here. And it's also open. And I will connect these 2 points. So this is the graph of y equals 2x from 0 to 5. After 5, the graph is x plus 6, y equals x plus 6. At 5, I needed to see at 5. Replace x by 5. At 5, 5 plus 6 is 11. So 5 plus 6 is 11, is here. This is 10 and this is 11. And at 6 is 12. At 7 is 13. And the graph goes like this. So this is the graph of x plus 6 from 5 to infinity. So this would be the graph of this piecewise function. I hope you enjoyed the lesson. Have a nice time and study hard.